So in the previous subsection, subsection 10.1, we went through an example of using Bayesian statistics, where we started with a prior belief, we collected some data, and then we updated that prior belief to a posterior belief to tell us what our beliefs are given the data we've seen. So what we want to do in this subsection is try and think more generally about what is the framework we use there, and what's the general idea of Bayesian statistics. So one of the first things is we had this kind of model for the data, right? Which is that we said we were going to toss the coin 4 times. So we were thinking that the 4 coin tosses were going to be, Bernoulli theta, and they were going to be IID. But the point was that this parameter theta, the probability of the coin coming up heads, we don't know that. So parameter theta is unknown. You might remember that back in the end of section 6, no, the end of section 5, end of section 6, I think we talked a bit about the idea of parametric families as models for data. You might want to remind yourself about that. So the idea was we had this model for what our data looked like, which was we knew it was going to be a Bernoulli distribution, and we knew we were going to take 4 IID occurrences of this Bernoulli distribution, but we didn't know what the parameter theta was. And so the goal was to learn about the parameter theta. If you remember, a Bernoulli theta is 1 with probability theta. We're letting that denote heads. And a 0 with probability 1 minus theta. We're letting that denote tails. So we had a p xi given theta is, well, there's actually a convenient way here of writing 1 if theta if x is 1 and 1 minus theta if x is 0, which if you think about it for a moment, that actually works, right? Because if you put in x equals 1, that equation comes out as theta. If you put in x equals 0, that equation comes out as 1 minus theta. So hopefully you can see that really is the probability mass function for a single Bernoulli distribution. Maybe I should just note that 1 is heads, 0 is tails. And so for our 4 pieces of data, x underlined being x1, x2, x3, x4, this was the product of all these. The xi should have had i's up there, shouldn't I? 1 minus theta. So 1 minus xi, which comes out as theta to the sum of xi. 1 minus theta to the 4 minus sum of xi. So that was our model there. Statisticians sometimes call this the likelihood. This kind of probability of the data given the parameter. Statisticians often call that the likelihood. So the thing we started with was we had this model in the terms of a likelihood. And we also came in with our prior belief, where we're going to write pi of theta for our prior belief about the unknown parameter theta. About the unknown parameter. And so in our particular case, we said that we thought it could be 0.2 with probability 0.2. We thought it was most likely to be 0.5 because I said that my coin looked pretty normal to me, but I was still entertaining the possibility that it was one of the fake ones from the joke shop. So that was the prior belief we had. Pi 0.2, pi 0.5, and pi 0.8. And then in pi here be the prior belief about the unknown parameter. And we thought that pi of theta was 0 otherwise. Then what did we do? We collected the data. And so in this case we saw heads, which were denoting 1, then heads, which were denoting 1, then tails, which were denoting 0, then heads, which were denoting 1. And then we use this to find the posterior using Bayes' theorem. So then we were looking for like the probability of the parameter given the data. And we said that by Bayes' theorem, this is the prior probability times the likelihood over px. But in fact, if you remember, we did this trick where we didn't actually work out the denominator. We worked it out later. So you can kind of write this as proportional to pi of theta px given theta, and use our trick that, well, we know this thing's got to add up to 1, so we can find out the denominator in the end if we need to. And so we ended up with our beliefs about p theta given x. So these came out as the posterior probability of 0.2 given our data became 0.26. Posterior probability of the fair coin given our data came out as 0.633, and the posterior probability 0.8 given our data came out as 0.346. So that was kind of the general framework. And so this is the same general framework that we can adapt whenever we want to do something with Bayesian statistics. So instead of starting off with, we might be doing exactly 4 Bernoulli trials, but more generally up here, we instead, in fact, want, we're collecting some data. We're going to plan to collect some data, x1 to up to xn, and normally they will be IID trials, and so we will have a likelihood, which is the product of the marginals. So p x given some unknown parameter theta being this product, because that IID, that's for some unknown parameter. So this can be either a probability mass function if we're in discrete, or a probability density function if we're in continuous. Either works. Everything we talk about Bayesian can work for probability mass functions if we're doing discrete things, or probability density functions if we're doing continuous things. We can also have a discrete likelihood with a continuous parameter, or we can have a continuous likelihood with a discrete parameter. We can kind of mix and match and everything works out fine. In our previous example, it was discrete, for example, but later on we'll be doing discrete continuous and continuous. And so generally, our prior was just some pi of theta being prior probability that the unknown parameter equals theta. And again, this could be a PMF or a PDF, depending on whether we think the parameter theta is discrete or continuous. Then we will collect some data, which will just be some x bar being x1, x2, xn. And then we will use Bayes' theorem to calculate it. Note that this, if we think here we've got posterior, there we've got prior, there we've got likelihood. So you can kind of summarize this as posterior is proportional to prior times likelihood. Remembering that likelihood is the name we used for this model here at the top. So Bayes' theorem allows us to write posterior is proportional to prior times likelihood. So that's the kind of, and again, the posterior will either be a probability mass function or a probability density function, but it will be the same type of thing as the prior was. If the prior was discrete, the posterior will be discrete. If the prior was continuous, the posterior will be continuous. But everything will work out well, and we'll find the constant by remembering that everything has to add up to 1. So that's the general framework of Bayesian statistics there. The main goal of this section will be to give 2 bigger, complicated examples of Bayesian statistics. However, there is one final distribution that we will want to introduce first, called the beta distribution, And that will be what we look at in the next subset.